favor. Good afternoon, everybody. Welcome to the Pedro Nunes lecture at University of Lisbon. This is the third lecture that Professor Bourguignon is doing in his tour in Portugal in 2016. The Pedro Nunes lecture is an initiative of Centro Internacional de Matemática in cooperation with Portuguese Mathematical Society that started about 8-9 years ago with a grant of Fundação Gulbenkian, is now continuing with support of the research centers that host these 3 lectures. Started last week in Aveiro, in Porto, and today is in Lisbon with the support of the Centro de Matemática e Aplicações Fundamentais de Investigação Operacional and the Centro de Análise Matemática, Geometria e Sistemas Dinâmicos from the University of Lisbon, both. And today we have Professor Bourguignon, that is well known from both of you, and is initially trained as an engineer for École Polytechnique and a PhD in Mathematical Sciences from Paris 7. And being for a long time, being always based in CNRS, but also professor at École Polytechnique, and director for about 20 years of the Institut de Hautes Études Scientifiques in Bourg-sur-Yvette. And it's since January 2014 is the president of the European Research Council. But he was also one of the participants in the foundation of the European Mathematical Society, which was president, because he was also president of the Institut de Mathématiques de France and the European Mathematical Society, and is one of the distinguished geometers of the recent decades, and will speak today. And this talk is a very appropriate connection between geometry and mathematical physics. And the topic is there, connecting Spinor fields and Dirac operators to geometry. And it's a great honor to introduce Professor Bourguignon. Pierre.
Thank you very much, Jose Francisco, for this nice introduction. It's my pleasure to give this indeed third lecture of this series of Pedro Nunes lectures here in Portugal. The topic today is really a topic which, in a sense, is a typical situation for mathematicians. That is, it takes them a long time to take what physicists do seriously. So I'm trying to show you that what happened should have happened more quickly, but now really a lot of things have happened, and in both directions. So actually, my purpose in this lecture is really to support the following point of view, that the use of spinors by mathematicians should lead to a geometry of its own, in particular shed light on numerous questions traditionally considered in Riemannian geometry. But actually, I could also think about more general geometries than Riemannian geometry. And therefore, I want to show you through a number of examples how to connect various notions related to spinors to a number of geometric questions and problems, and explaining why this really gives rise to the possibility for a new viewpoint. So just a summary quickly, very basic facts on spinors, because maybe not all mathematicians are comfortable with spinors. And now I'm a geometer, so I want not only to do algebra, but I want to do geometry, differential geometry in particular. So you have to go over to manifolds and then therefore to study spin metrics on manifolds. Then the key element, as usual in differential geometry, that it's well known that some differential operators are playing a very critical role in the study of geometry. And in the context of spinorial geometry, the key operators are the Dirac operator, as we were told by Dirac, but also the Penrose operator. I will define it later on. And of course, I will start with the Dirac operator and the fact a number of things, properties, interesting properties on what one calls harmonic spinors, which are just spinors annihilated by the Dirac operator. Then I want to discuss some special spinor fields, in particular a lot in connection with what physicists call supersymmetry, and you will see that. But then there is another thing which took a long time actually to be unraveled, although it was present from the first day, which is the fact that spinor geometries, spinors and spinor geometry altogether are very much, have a very peculiar behavior in terms of conformal changes of metric. That is, of the metric, you just change the notion of length pointwise. And actually, there are really some nice properties of conformally covariant operators in relation with the Dirac operator. And then I will try to draw some conclusion. Maybe there is a bit too much on the plate, so I hope we can still do it without making you too exhausted at the end of the lecture. So let me start with basic facts on spinors. So now the very modern way of talking about spinors, which is now really well established, is to start with a vector space and on which you give yourself a Euclidean metric, a Euclidean scalar product. Of course, you can do it with a general metric, a general scalar product, which doesn't have to be positive definite. And therefore, you can, to such a data, a vector space and a scalar product, you can attach the so-called Clifford algebra. And the Clifford algebra is very simple. You just think of any possible tensor you can consider, but you want to force upon this the relation that x squared, x being a vector, is minus the norm of x squared. And therefore, it means that, and of course, the bracket you see there means I'm taking the bilateral ideal generated by these elements. So it's very easy to see from this relation that automatically the Clifford algebra is a very peculiar structure because, of course, you have the scalars, because you start from a tensor algebra. You have the vectors, which are basically not affected by the relation I wrote. But then as soon as you get to second-order tensors, clearly, I mean, because of this relation where we said the norm square, the square of x as a tensor product is minus the norm squared, automatically it shows that what's left is basically only the skew symmetric part, because the symmetric part goes back to scalars in some way. And then it goes on like this. So, of course, the key element is to classify these Clifford algebras, and it's much simpler to classify them over the complex numbers than over the reals. So over the complex numbers, their structure is extremely simple. There is some kind of a very peculiar twofold periodicity, which means that if the dimension is even, so n is the dimension of my n-dimensional vector space, then the Clifford algebra is actually a simple algebra, and it's known that simple algebras are always endomorphism algebra of a certain vector space. And in the case of odd dimensions, then the Clifford algebra actually is not simple anymore. It's a direct sum of two simple algebras, so endomorphisms of some vector spaces, sigma v and sigma twiddle v. And actually, both sigma v and sigma twiddle v are the spaces of spinors. And they are, of course, very simple because the Clifford algebra in dimension 2m, from what I said, is actually algebraically as a vector space isomorphic to the exterior algebra. But of course, not as an algebra. It's a much more sophisticated algebra than the exterior algebra. Actually, the exterior algebra is just the algebra you obtain if you take G equals 0. But so my point is, of course, the dimension of the Clifford algebra is 2 to the n. And therefore, if n is 2m, then the dimension of the vector space of which the endomorphism is the Clifford algebra is 2 to the m. And the same way, the same calculation applies to the Clifford algebra in odd dimensions, and therefore you find this. And actually, it's very clear from this definition already that the dependence of the spinors upon the metric is quite implicit, because it's very easy to see that if you have an algebra which is an algebra of endomorphism of a certain vector space, then of course, very easily from the algebra you're going to unravel what are really the projectors in this algebra of endomorphism on lines. But if you want to single out on this line a very specific vector, that's much more complicated. So what is very easy to construct is the projective space over the spinors, but the spinors is a more subtle object. So this is really something I'm going to come back later, because it really was a problem which was hanging around for many, many years. How do you follow the change of the structure of the spinors when you change the metric? So the spinors are vectors in a fundamental representation of the group spin n, and which is the double cover of SON. So SON, if you take n larger than 2, SO2 is very peculiar, it's just the circle. and therefore its universal cover is actually R, and it's an infinite cover. But SON for n at least 3 is a group which is not simply connected, but there is just a twofold cover which is simply connected, which is spin n. And the link between this, this definition of spinors, which a priori is independent from the one I gave, because I claim here spinors are vectors in the fundamental representation space of the group spin n. The link with the Clifford algebra goes as follows. Actually, from my vector space V and the metric G, I can define the group spin G, which you can obtain as the multiplicative subgroup of the Clifford algebra, which stabilizes V. So you insist that all elements acting on vectors in the Clifford algebra are actually giving, again, a vector. But on the other hand, you also insist that this should be some kind of normalization. And of course, as soon as you have this spin VG, which is inside the Clifford algebra, you can always use the adjoint representation to have spin VG acting on V, because by definition, I said that spin VG was stabilizing the image of V. So this is the way you get actually the spin group acting on the vectors V, and actually very easily you prove that this spin VG is actually isometries, acts by isometries on V, but it doesn't act as SON, it acts as a double cover of SON. So this is the key element. Now there is an extremely important notion in spinors, which is so-called chirality. And what is this? So let's assume for the moment we are working in even dimensions, which is of some interest. And then you can look at, of course, among the, I said that the Clifford algebra was really isomorphic as a vector space to the exterior algebra. So in particular, in the Clifford algebra, I can look at the action of the volume element determined by G, which is an n form, n exterior form. And I'm working with complex numbers, so to make things really nice, I multiply by square root of -1 to the m. So remember, I'm in even dimension, so n is 2m, and m, I'm taking the mth power of square root -1. And then it's easy to see that if you have this action, automatically this action is actually an involution. And it's well known for involution that there are only two possible eigenvalues, +1 and -1. And then you just do the decomposition of the space of spinors into half spinors, positive, the ones for the eigenvalue +1 for this normalization, and the negative spinors, the one with the eigenvalue -1 for this action. And they are what one calls the half spinors. And of course, the dimension is, since sigma v was a dimension 2 to the m, so the dimension of the space of half spinors is 2 to the m-1. And of course, it's very obvious by construction almost that the Clifford multiplication by any vector in V actually maps the positive spinors to negative spinors and conversely. Okay, so this is a chirality. And so now maybe just a general comment on why are or how are spinors different from objects that mathematicians or geometers are used to work with. Well, the first point is that usually when one works with vectors or exterior differential forms, then one is usually, I mean, they carry some kind of a dimension. A vector is one-dimensional, two form tends to be connected to two-dimensional objects and so on and so forth. So in particular, the exterior algebra is very much related to the Grassmann algebra, and therefore discussion of subspaces. But in the case of spinors, this is quite different. And actually, one of the things which remain open for a long time, which I will discuss a bit later, is the fact that comparing the spinors for different metrics, of course, these vector spaces are always isomorphic, but imagine you have a family of metrics and you want to see how the family of spinors is evolving, then it's a non-trivial question, which actually in the literature you find a number of wrong references to this and actually wrong formulas for this. So finally, with Paul Gauduchon, I think we proposed a systematic approach. And of course, another thing which is very important for later on in the lecture, imagine you replace a metric by a conformally related metric, which means I just use an homothéty to if I'm doing algebra, I just take G and multiply by lambda, lambda being a positive number. Then you can really very explicitly compare the spinors in this case. It's very simple to see how the two Clifford algebras compare. You can really build an explicit isomorphism. And actually, if you are used to work with weights, that is, instead of working with vectors, but you think of vectors having some kind of a weight attached to them, then you can really actually construct spinors which are completely invariant by when you change a metric in the conformal class, which means that there is actually a notion of conformal spinors, but they are not completely, I mean, they are associated to vectors with a weight, and the weight can be computed explicitly. This was done by Nigel Hitchin. So in a sense, this is just to always to make you feel that spinors, which are so fundamental in physics, actually mathematicians felt a bit awkward with because they didn't correspond to objects they were used to work with. So let me move on now to, I've done some basic algebra. I want to move on to some differential geometry. And of course, the purpose, because I want to do differential geometry, is to be able not to do just algebra, but to do that globally on a certain manifold. So in a sense, what will replace my vector space and the metric on it, or scalar product on it, will be a manifold M, and on it, a Riemannian metric. I'm going to stick to Riemannian for the moment, although of course we could do Lorentzian geometry if we wanted, but let me stick to Riemannian in this case. And now the construction is, the usual tensor fields are very simply constructed. If you have a manifold, you know very well its tangent bundle, which is the collection of all vectors over M. So if M is n-dimensional, the tangent bundle is a manifold of dimension 2n, because you have the n coordinate, local coordinates, and then above each point you also have the n dimension of the tangent space. But you also have the cotangent bundle. So if you take any kind of tensors, you can always take the tensor product of these bundles, which gives you the appropriate setting for the geometry. Another equivalent approach, which took some time in the 1930s to be established, is the fact that you can actually rediscuss everything I said from a slightly different point of view, which is instead of really already working with the tensor bundles and or tangent bundle or cotangent bundle, I could also immediately jump to the so-called bundle of orthogonal frames, which I call SOG of M. So that is, above a point, you put a copy of the special orthogonal group. So I assume my manifold is not only Riemannian, as I said, but oriented. And what do I do? Well, over each point, I just put all basic. Did I touch it? Oh.
Yeah, I don't think people.
Okay, so we changed the instrument. So another equivalent way of looking at this is, of course, to use the construction of, that is to put above each point the collection of all G orthogonal bases which are direct. So I put above each point a copy of the group SON. And then this can be done in a very, I mean, a very natural way. And the advantage of this approach is, of course, I do have an action of the group SON on this SOGM. So of course the dimension is now the dimension of n plus the dimension of the group. But in a sense, the difference between since there is no privilege based at any point, all bases are equivalent, and the way you exchange them is by just letting the group SON act. And of course, you can very easily construct it from the following way, but then the key point is that you can use this construction in the opposite direction. Namely, you can really, from this principal bundle, we call it principal because we have an action of the group SON on this total space, then you can use the so-called associated bundle construction. And this associated tensor bundle construction is the following one. Anytime I take a representation of the group SON acting on a vector space R capital N, big dimension, then I can really form the product of the bundle of bases with this Rn. And then I take the equivalence relation, which is a very simple one. I take a base, I take a vector in this R capital N, which is a space on which SON acts. And then I declare equivalent, of course, what you can imagine, namely that if you take another basis exchanged by SON, then you, of course, do on the vector xi sitting in R capital N just the opposite transformation. So this is really the key way you can, for any representation of SON, construct a new bundle which is obtained by this construction. And of course, now I want to do this with spinors, and of course the key element is that I have to replace everything I said with SON with spin N. But the difficulty is the following one, is the fact that I can find a spinoidal metric, which I will call a spin N principal bundle gamma. So I want now a bundle of on which the group which will act is going to be spin N, but I want the group to act really freely. I don't want to act as SON, which means I would have a double cover. I don't want this to happen. And so if I want to do that, then I have to go back to my fundamental sequence, which says that for n at least 3, spin N is a double cover of SON. And then it's well known that if I look at all SON bundles, how can I relate them to spin N bundles? Well, I cannot always do it. There is a cohomology sequence attached to this sequence of algebras, which prevents this to happen. And if you analyze this cohomology sequence from this exact sequence, you realize that in order to be able to define globally spinors on a manifold M, you need the W2 of M, the second Stiefel-Whitney class, which sits in the 2 cohomology of M with coefficients in Z over 2Z to vanish. And if this is not satisfied, you just cannot globally define spinors on a manifold. And of course, if this is satisfied, that is, if Wm vanishes, then you say that M is a spin manifold, and then you can find indeed a spin structure that is a choice of a spin N bundle. And how many such spin structures are there? Well, the ambiguity is again readable from the exact sequence, and it's exactly connected to the first cohomology of M in coefficients, with coefficients in Z over 2Z. So this means, in particular, if the manifold is simply connected, then you have uniqueness of the spin structure, if there is one. And of course, now, how do you build the bundle of spinors? Well, in a very simple way, very similar to the one I described. That is, I have a principal bundle gamma, which is a principal bundle on which spin N acts. Then I use the fundamental representation of the spinors, sigma N, and I do this associated bundle construction. And therefore, I get what I call sigma gamma of M, which is the bundle of spinors associated to the spinoidal metric gamma. And actually, it's very easy to see that by almost construction, the group of the Clifford algebra attached to G, which, I mean, is at each point acts on the tangent space, actually acts always on sigma gamma of M, that is the bundle of spinors, using the pointwise Clifford multiplication, which is the way I could connect the Clifford algebra and the spinors. So this is the fundamental basis for the study of spinors on manifolds. You see, so the bad surprise or the interesting point is that you cannot always make sense of spinors over a manifold. You have a topological condition. But when you can, there may be several spin structures, and therefore you have to declare which spin structure you have chosen. But then you can do things. So now natural operators on spinors. The first element, which is very important, which actually was understood reasonably quickly, was the fact of suppose I have my spinorial metric gamma, so I have my bundle of spinors, the spin gamma of M over M, and the key point, that's my principal bundle, I'm sorry for the moment, and so I want to say that I want to be able to compute derivative of these people, sections of that bundle. And actually the way you do it is go back to SOGM, and you know that pointwise spin gamma of M is a double cover of SOG of M. So there is a natural map from spin gamma of M to SOG of M, which pointwise is a double cover. And since you can define the Levi-Civita covariant derivative, which is the basic ingredient to compute derivatives in Riemannian geometry, you can think of it as a form defined on the bundle of principal, the principal bundle of a basis, taking its values in the Lie algebra of SON. Then it's very easy to see that since I have my double cover from spin gamma of M to SOG of M, if I pull back this form, I get again one form with the right properties, mapping in the Lie algebra. So it was mapping in the Lie algebra of SON, but the Lie algebra of SON and the Lie algebra of spin, they are the same because there's just a twofold cover. But of course, you have to remember when you do this identification of the two algebras, there is more or less a factor 1/2 involved there because there is a double cover hidden there. Nevertheless, just by using this very simple pullback construction, it shows that I can define a covariant derivative on the bundle of spinorial basis, and therefore I will be able to compute covariant derivative of any kind of spinor field. So therefore, it's now I'm coming to the notion of general notion of operators which will be acting on spinors. So let us just go back for 1 minute to a general situation where I have a vector bundle E. Then what are the covariant derivatives? They are just the operators, which are first-order operators, mapping sections to this bundle, that is mapping points in M to elements in the vector bundle E, to one forms on E, with a property that if you look at the principal symbol of such an operator, so a principal symbol, it's a first-order operator, so I have to take my bundle E, tensor it with T star M, because it's a first-order differential operator, and takes its value in the bundle in which the mapping takes its values, which is, again, T star M tensor E. And a covariant derivative is exactly an operator, differential operator, which has the property that its principal symbol is exactly the identity map from T star M tensor E to T star M tensor E. And therefore, it's the basic consequence of that, the translation of this algebraic description I gave for the definition of a covariant derivative is the following one. It says that if I take any function f on the manifold, if I take any section of my bundle E, the covariant derivative of fs should be df tensor S plus f covariant derivative of S. This is exactly a translation of what I said about the principal, the principal symbol. So either you take it as algebraically as I defined it there, or you take it as a formula for computing derivative of multiplication of a section by a function. And of course, for spinor fields, I said I have a covariant derivative. And so if I take a spinor field psi, which is a section of the spinor bundle, of course, that is a spinor varying with the points, then I can compute its covariant derivative, knowing that it's a spinor field for this metric gamma. I will call it d gamma psi, And so this, just by copying what I said and using the definition at the top. So now, the natural operators on spinor fields are very simple in the sense there are only two universally defined operators on spinors. And the reason why there are only two universally defined is because imagine, so now in my case, my vector bundle E would be the bundle of spinors. And so I'm supposed to look at maps from, remember what I said here? Here I said I have to look at maps from T star M tensor my bundle, taking value into some bundle. So now if I do this with a bundle of spinors, then if I want to have a universally defined operators, it means have to have something which is equivariant for the action of the spinor group. And then actually, if you do that, you see that this space, T star M tensor sigma M, has only two invariant subspaces under the action of the spinor group. So the only space to which I can map it universally without adding any other information is actually corresponding to these two cases. And the two subspaces you find, there is a copy of what of the spinors themselves, and another space which is the so-called 3/2 spinors. For physicists, the sigma, gamma m are 1/2 spinors. And therefore, to get natural operators, I just look at the projection from this T star M tensor sigma to these two factors. If I do the first projection, the explicit formula to do this projection is the one which is written there, and this defines the so-called Dirac operator. So the Dirac operator for the metric gamma applied to psi is exactly the following construction. You take psi, compute its covariant derivative in direction EI, and then you Clifford multiply with EI, and EI is any orthogonal basis on the tension space. Of course, the key element is to prove, but that's easy, that if you replace this orthogonal basis by another one, you get the same result. So this is the Dirac operator, and of course the Dirac operator maps spinor fields to spinor fields. You get a new spinor field. And now the second factor, so I told you that T star M tensor sigma M decomposes into the direct sum of two factors. The other one is slightly more complicated to introduce. It was introduced by Penrose. It's a so-called twister operator or Penrose operator. And so it maps spinor fields to spinor fields, more complicated spinor fields, which are spinor fields tensored with one form. And the formula for that, I use the letter P for Penrose. So the Penrose operator applied to psi in a direction x is dx gamma psi, the covariant derivative, plus a correction term, which is 1 over n, x Clifford, the Dirac of psi. And so this is well defined. I do get on the right-hand side a spinor, and I get a spinor anytime I give myself a vector. So this is really something like a one-form tensor, a spinor. So this is the two natural operators existing on spinor fields, universally defined. So anytime you have a spin manifold, you can make sense of the Dirac operator, you can make sense of the Penrose operator. So this is the situation. And so now the very important properties of the Dirac operator is the very simple fact that the principal symbol of the Dirac operator is Clifford multiplication. So therefore, there is no surprise that if you apply it twice, that is, if you get the square of Dirac operator, you get twice the multiplication by the cotangent direction, but psi Clifford psi is exactly minus the norm squared of psi by the formulas in the Clifford algebra, and therefore it shows that the square of Dirac is a Laplacian, just by having as leading symbol. It's easy to see that it's self-adjoint for the metrics given by the metric. And actually, it's also very easy to see from the definition that in even dimension, it has the property of exchanging the chirality. So if I take a positive spinor field, d psi will still be the d, the not curly d, but the straight d, by the covariant derivative will still be a spinor field of, say, positive type, but I Clifford multiply by EI, so it makes it a negative spinor field. So the key point is that the Clifford operator, Dirac operator, I'm sorry, exchanges the chiralities, which means that if you look at an eigenspinor for Dirac, it must contain really components, negative and in even dimension, must have positive and negative components unless it is in the kernel. And there's a wonderful formula which was first discovered by Schrödinger in the late 30s, but rediscovered by Lichnerowitz 1960, which is the following one, which gives you the explicit value of the square of Dirac. So in a sense, what I said before is that I said that at the top level of the symbol, the square of Dirac is like a Laplacian, but the exact formula is this one, which means it's, if you compare the square of Dirac, which is a Laplacian, with the most obvious Laplacian, which is just taking covariant derivative composed with its adjoint, then there's a correction term, and this correction term is a very, very simple one. It's 1/4 the value of the scalar curvature of the metric, that is the simplest possible curvature invariant of the metric. It's a function times psi. So in a sense, Dirac squared is the obviously positive Laplacian d gamma composed with d gamma star, and then corrected by 1/4 the scalar curvature. And this formula has a number of extraordinary consequences, which I will discuss later. So harmonic spinors. So harmonic spinors, as I said, they are just spinors which are annihilated by Dirac. And if you're on an n-dimensional manifold, I will just denote the space of harmonic spinors by H, curly H, M. Of course, the dimension is 2M. It's very simple to see that there are two types of harmonic spinors, the positive ones and the negative ones. And actually, you can even do some more sophisticated theory. I said I would be working with the complex structures all the time, with the complex spinors all the time to make things simpler. If you are working with real spinors, actually the periodicity is not anymore a periodicity of 2, but it's a periodicity of 8 with the remainder for the division by 8, which tells you a number of things. So in particular, if you look at this more refined structure using real spinors, then in a dimension which is congruent to 4 mod 8, then you realize that actually this H plus of M, the positive harmonic spinors, H minus 1 of M, the negative harmonic spinors, are actually even dimensional spaces. So actually it gives you further information on the harmonic spinors. The very critical element which really changed the mind and the attitude of mathematicians and maybe led them to rediscover spinor fields was really the Atiyah-Singer index theorem. Because Atiyah and Singer identified that actually the Dirac operator, or even I should say, in even dimension, the positive Dirac, that is the restriction of the Dirac operator to positive spinors, actually really led them to a very fundamental statement. So imagine now you have a manifold whose dimension is a multiple of 4. So of course the first case is dimension 4, 8, 12, and so on. Then the index of this half Dirac, I mean the positive Dirac, I could say the same thing with the negative one, it would just be the opposite. Then it's the dimension of the positive harmonic spinors minus the dimension of the negative harmonic spinors. So usually the index is the dimension of the kernel minus the dimension of the co-kernel. But in this case, it's very easy to see that the co-kernel is just negative spinors. And then they showed that in this case, I'm assuming the manifold is compact, then you get a very interesting topological invariance, the Heroof genus. And the fact that you have for the index of the Dirac operator in 4K dimension, this topological property is of course extremely important. And the way they got at this was, of course, because they realized in particular that the Dirac operator was in the sense generating all possible elliptic operators on manifolds. So this theorem can be sophisticated in many different ways. Of course, it says that if M has a non-vanishing Heroof genus, any spinorial metric will have necessarily some harmonic spinors, because if this Heroof genus of M is non-zero, the index is never 0. So it shows there are always harmonic spinors, either positive or negative. And also, actually, you remember the formula I reported, which was due to Lichnerowitz and Schrödinger. Remember this formula. So imagine you have a harmonic spinor. So of course the left-hand side will be 0 because it's already killed by d gamma. So it's of course killed by d gamma squared. And then of course the next term, as I said, is a positive operator because it's the composition of an operator and it's a joint, and my metric is positive. Therefore, if I take the scalar product of this, the global scalar product of the manifold of this equation, I get 0, because I take a harmonic spinor, equals something positive, because that's the integral of d gamma psi squared, plus scalar curvature times psi squared. But psi squared is positive, so if the scalar curvature is positive, this is impossible, because I get a harmonic spinor, so I have 0 on the left-hand side and the sum of 2 positive terms. So this is really the very important contribution. So it was really, actually, that's the reason why Lichnerowitz used this formula, and he proved that if you have a manifold which has a non-vanishing A-roof genus in dimension 4k, then you cannot have a metric of positive scalar curvature on it, which, you know, having a metric of positive curvature was always considered as a very weak property, because scalar curvature is a very weak invariant of the metric. So all of a sudden, there was really a topological abstraction for the existence. Remember, the manifold has to be a spin manifold. So, of course, which is not always the case. For example, if you take the two-dimensional complex projective space, it's not a spin manifold, and therefore it has, although its equivalent of its A-roof genus is non-zero, it doesn't meet metrics of positive scalar curvature. Okay, so now the study of manifolds admitting metrics with positive scalar curvature has been immensely enhanced by this link, and there have been many different strategies. So maybe I pass quickly on this. Some people have been using surgery to show that one can, using the structure, topological information on the spin cobordism group. Then Gromov and Lawson have really proved a number of results on the case where the manifold is simply connected. When the manifold is non-simply connected, a totally different approach by Gromov and Lawson, again, really looking at maps from manifold to another one, which led to extended notions of A-roof genus. And of course, they could discuss existence of metric of positive curvature. And finally, the final word came from Stefan Stolz in the late 80s, early 90s, who really used fully the information on the spin Bordism group to really show that you can completely reduce the question of existence, no matter what. That the manifold can be simply connected, non-simply connected. You can completely reduce it to a purely topological question. So this is an interesting situation where a geometrical problem, which looks like a very geometric one, whether a manifold admits a metric of positive scalar curvature, actually can be completely described in topological terms. And the way you get this is through the Dirac operator, and of course through the sophistication of the Atiyah index theorem. So now, concerning the dimension of harmonic spinors, what I've been discussing is some cases in which you are sure there will be some harmonic spinors because there is a topological constraint. Actually, Nigel Hitchin in his thesis in the early 70s already showed that when you change the metric, you can make the dimension of the space of harmonic spinors change. So, for example, he showed already that you can have, well, again, it has to do with, as I said, the theory of real spinors and the eightfold periodicity. So concerning the congruencies mod 8 of n, either 0, 1, or 7, then you can find metrics which have non-trivial harmonic spinors. And it's very interesting if you take the so-called Berger metrics on S3, which are very simple metrics. So you can think of S3 as fibered over the two-sphere with fibered circles, which is a very basic geometric construction that people like to do. But then one thing you do, you shrink universally with the same factor the fibers. And here, in this way, you get a family of metrics on the three-sphere. And then Hitchin showed that when the circles get very, very small, actually the number of harmonic spinors grow, and actually you can show that this number can be unbounded. Of course, for a given manifold, a given metric, it is bounded, but when you vary the metric and you make it degenerate, you can get more. And actually, this construction was later on carried over by Christian Baer to many more manifolds. And also the case of 4K dimensional spheres was also, people could show that always there exist harmonic spinors. Although the Eruff genus, of course, is zero. So even in this case, you can show that there are metrics for which there are harmonic spinors on the 4K sphere. So maybe I will pass quickly on this because many more work has been done, and really because what I discussed before was really more, I was concerned in showing that there are at least some harmonic spinors, but you can also ask yourself, when there are topological constraints, are there actually metrics which realize this lower bound? And actually this was done in a number of cases. So in lower dimension, for simply connected manifold, and then many other cases, and actually even generically, you can prove that the generic Riemannian metric has actually the minimum number of harmonic spinors on a manifold, a given manifold. Okay, so now I'm coming back to this question of varying the metric, which is something which really was left open for a number of years and actually led to a number of formulas which are not exactly correct. So the purpose here is to say, can one describe how one changes metrics in a way which really allows you to compare orthogonal bases? So the first step before going to spinorial basis is to work with just normal orthogonal basis. And actually, one way of thinking of a basis, which is very useful, is the following one. So imagine you think of a G orthogonal basis as a linear map from Rn, which has a preferred metric, namely the usual Euclidean metric, to the vector space V. And of course, claiming, asking B to be G orthonormal is exactly saying that the inverse, so B is a map from Rn to V. So it means if I take B minus 1, my map is invertible. It's a map from V to Rn. And then if I pull back using B minus 1, the Euclidean metric, I want this to be G. So definition of a G orthogonal basis is just a linear map from Rn to V with this property. And of course, all G orthogonal bases can be obtained from the basis B just by composing on the right. You remember B is a linear map from Rn to V, so composing on the right means I'm using just a usual matrix, orthogonal matrix in Rn. Because On is exactly the group of E isometries in Rn. And so now, imagine I introduced a quantity Hg, which is G minus 1H, which is the following one. So G for me is a bilinear form. G minus 1, of course, is a bilinear vector, so it's something which is a 2 times contravariant. And then if I compose them, I get a linear map. And of course, if you want what I'm doing, I'm just transforming my symmetric bilinear form H into a matrix by using doing things in an orthogonal basis for G. So this object, capital H sub G, is a linear map from V to V, and it has the property by definition that evaluating H over 2 vectors is the same as doing what I wrote there. Just applying, I'm just writing the definition of HG. And now, so now the correspondence which I was mentioning above, which is establish a natural correspondence between G orthogonal basis and H orthogonal basis, is just the following one. So I take a basis B, which is G orthonormal, and attach to it the quantity which is written there. So remember, Hg is a map from V to V. B is a linear map from Rn to V. So if I compose on the left with a map from V to V, I do get a map from Rn to V. And it's very easy to see if you do such a thing. And of course, the key point is to be able to take the square root of Hg, or minus the 1/2 power of Hg, but you can do it because of the fact that G and H are a scalar product. And then the key point now is to, of course, to establish that you do have a nice equivalent equivariance under the action of the orthogonal group. But this is not a problem because you know everything I've been doing here, I've been doing by composing on the left. And remember, the action of the orthogonal group is on the right. So, and of course, yes, so I said HG is well defined. So in this way, I have defined a natural correspondence between G orthogonal basis and H orthogonal basis, which is equivariant for the action of the orthogonal group. And of course, now, how do I go to the spinoidal setting? Well, one still needs a little more geometry. So you have a natural bundle, which is the bundle of invertible linear maps from Rn to V, which, as you remember, I think of them as bases. And I can map it to the space of metrics on V, which is the very simple way, which is, of course, if I take such an invertible map, then, of course, I attach in the construction I did before, the metric which is transposed from the Euclidean metric using B, of course. So this is my map from a basis to metric V, which is, I declare the metric for which this basis is orthonormal. And so now if I put myself at invertible maps from Rn to V, so I take a basis, then the tangent space to this space can be split. It's very naturally identified with the linear map from Rn to Rn. And now the very quick element is that which are the vectors tangent to invertible map from Rn to V, which are mapped to the same metric. It's very simple to see that they are exactly the symmetric matrices. And therefore, a space which is transversal to the vertical objects, the ones which maps for this projection, are exactly typically the skew symmetric maps. And therefore, now I can do the following thing, because I have a very nice distribution of horizontal spaces in this projection. So it means that any curve joining G and H on the space of metrics, for example, I can take the very natural segment, that's the most obvious one. Actually, I can lift it to the invertible maps from Rn to V because at each point I take the velocity vector of my curve, I lift it to the horizontal space, and then I start from a certain basis, and then I follow the integral of this path lifted. And therefore, I define in this way I define this way a transformation from a basis which is G orthonormal for H to a basis which is G orthonormal for G, a basis which is G orthonormal, and to a basis which is H orthonormal. And therefore, it's very easy to see that if you do this for this most trivial path between G and H, actually you do get the map I defined before. And of course, this definition is very interesting for the reason that because I'm using only arguments of lifting, remember the spinoidal basis is a twofold cover of the orthogonal basis. Therefore, my argument of lifting can be actually done on spinoidal basis because the same arguments apply. So it means this way I can really, in a canonical way, associate orthogonal bases which are spinoidal for G in a natural way to bases which are spinoidal for H. So this can be done really, so this gives rise for two spinoidal matrices gamma and eta to, if I use the same spin structure, of course, if not I can make sense of anything, a certain transformation, and therefore I can really map the spinor bundle for gamma to the spinor bundle of eta, because I do this point by point. And of course, there is one case where you can do that much more simply. It's the case where you have just conformal relation between H and G. So that is, there is just a scalar factor between them. And in this case, the transformations are just multiplication by A minus 1. Of course, the covariant derivative of G and H are different. So therefore, if you look at the formula for the Dirac operator, it's a much more complicated formula. So in a sense, the operator which I call d eta, which is the Dirac operator for eta, but transmuted by gamma will be given by this. So what I do, I take a gamma spinor, I make it an eta spinor, so now the eta can act, and then I bring it back using this, okay? And of course, this formula says that this transmuted operator is not anymore a Dirac operator for gamma, because it uses the other things from the covariant derivative of eta. But still, so you have the nice formula, and then typically you can really do this for families of metrics, which of course is a very natural situation for geometry, but also for physics. And therefore, you can establish the formula which tells you the infinitesimal variation of Dirac, which is more complicated than what you would expect, which is this quite comprehensive terms, in which you have a mixture between different objects. So you have, you see, it's not a Dirac operator for the reason that here you have a kg of bi, so it's not Dirac. I'm computing the infinitesimal variation, and then a correction term, which actually is quite familiar. And as a result, one can study the variation of eigenvalues of Dirac operator. And of course, this is interesting. And here is the formula for that. So imagine you have a spinorial metric gamma. You deform it using a symmetric two-tensor field K, which is the deformation of the metric. Then the variation of the eigenvalues is given by this quantity here, which is the scalar product between the infinitesimal variation of the metric K times a certain quantity, which is this real symmetric bilinear form. And you see there appearing something which reminds you of the Penrose operator. So in a sense, the Penrose operator appears naturally when you look at the variation of eigenvalues of Dirac. So it's kind of interesting. And of course, there are several geometric aspects of this which are very interesting in this formula. Killing spinors. So I'm coming back to Penrose. So Penrose introduced, actually for the purpose of looking at the geodesic flow of the Kerr metric, some interesting object. He introduced a notion of a killing spinor. So it's a spinor field which is annihilated by the Penrose operator, but also which is an eigenspinor for Dirac. So you put two conditions on psi. That is, you ask that p psi is 0. So p psi of x is 0 for every x. And then you insist also that d psi should be lambda psi for a certain eigenvalue lambda. And the lambda appears here. So it's very easy to see when you combine the two conditions that a killing spinor satisfies this very strong equation that its covariant derivative is related to its value by the formula which you see there. Therefore, it's, one can prove from this formula very easily that if I look at the quantity psi sub psi obtained by doing this, that is, I take something like a quadratic quantity in psi, then it is a one form. But if psi is a killing spinor, this is automatically a killing field. That is an infinitesimal isometry. So in a sense, killing spinors are reinforcement of isometries. They are square root of isometries in some sense, because you have this. And actually, you can look more carefully, and the psi tensor psi bar as there are other components. Here I looked at the one-form component of this guy. So psi tensor psi bar more or less sits in the Clifford algebra. So it sits is an endomorphism on spinors. So an endomorphism on the, but the Clifford algebra is very similar to the exterior algebra. So you can look at the various components in the various degree of the form. So this was the one-form part, but you could look also at the three-form part. You can look at the five-form part, and so on. And physicists have introduced the notion of a supersymmetric transformation in the following way. So supersymmetric transformation are transforming fermionic fields, such as spinor fields, to bosonic fields, which are typically one forms. And one typical transformation is this one. So psi, phi, and psi are spinor fields. X is a vector. So of course, if to a spinor field, I attach the real part of the scalar product of x Clifford phi psi, then of course this gives me a supersymmetric transformation. Of course, phi is a generic spinor field, and psi is a specific spinor field. And it's very easy to see that if there exists a non-trivial killing spinor, automatically the formula for the curvature is very simple. Actually, if you compute the curvature, you think of it in direction of xy, you think of it as a two-form. So a two-form acts on the spinor field. It gives you the very simple expression that it is just the double Clifford multiplication by xy and minus yx. And actually, you can prove if there is a non-trivial killing spinor, automatically the Ricci curvature of the metric is actually a multiple of the metric. So the manifold is Einstein, the metric is Einstein, as one says. So just to finish with killing spinors, of course, there are many, people have been discussing this. So if the eigenvalue is 0, then it's very easy because then automatically the killing spinor is parallel for the reason that you look at this equation, if lambda is 0, it means dx psi is 0. So of course, if the spinor is parallel, it means the holonomy group of the metric is reduced. If lambda is purely imaginary, then you can prove that M is automatically non-compact. If lambda is real but non-zero, then the Ricci curvature is uniformly positive, and if the manifold is complete, if the metric is complete, the manifold is automatically compact. But then the key construction has been due to Christian Baer, and he does the following thing. Suppose you have a manifold M, which admits a killing spinor. You build over it the cone, that is, you multiply by R plus star, and you put a metric deduced from G, which is on the metric on M, in the most simplest way. That is, you do a cone construction. dr is the parameter over R plus, and you do the metric G bar on the cone, which is dr squared plus R squared G. Then you have to do a little bit of work, but it's very elementary, through identification of the action of spin n plus 1 with the Clifford algebra of CLG. Remember that depending on the dimension, even or odd, you have the Clifford algebra, which is simple, or a copy of two endomorphism algebras. Then you can really map spinor fields from the manifold M into spinor fields on the cone. And if you do this identification, then a miracle occurs, namely, that was really what Christian Baer did, was to notice that the killing spinor on M, that is the basis of the cone, becomes a parallel spinor on CM. So if you have a parallel spinor of CM, it means that you must have a reduction of the holonomy. And therefore, this has been fully discussed. Actually, Nigel Hitchin had already shown that this is connected to very special holonomy groups. And of course, imaginary killing spinors. The second case I looked at have been classified by Elgabaum. For real killing spinors, it's more complicated, but actually it has been done. So I'm skipping this just because it becomes a bit too technical. So now I want to discuss a little bit more about the geometrical physical point of view on manifold with killing spinors. Actually, in dimension 5, it was a result by Thomas Friedrich and Ines Katt that the only manifold which you can find actually are automatically with a very peculiar structure, which was also studied by physicists. But in dimension 4Q plus 3, which includes 7, for example, which doesn't include 7 because I want Q to be at least 2, so it starts with the 11. Then you have to have some other very peculiar structures, so-called Sasaki 3 manifold. And of course, the case left over was dimension 7. And of course, it's very interesting because if you have a 7-dimensional manifold, the cone builder will have 8 dimensions, and then automatically the holonomy you will get will be a spin 7 holonomy, which is a very special case. So one case which was very much studied by physicists in supergravity was the so-called squash 7 sphere, which gives you on the 7th sphere an Einstein metric. I told you anytime there is a killing spinor, there is an Einstein, automatically the metric is Einstein. But on top of that, it's not the usual one. It's another one which has a lot of interesting properties. And of course, it was, physicists have analyzed this situation extremely in great detail. So now I'm moving to my last part before my conclusion, which is the conformal behavior of the Dirac operator. So I already told you that if I take a metric G and a conformally related metric, then actually it was very simple to relate the spinors. But it's also very simple to relate the Dirac operators. And this is the formula which actually was due to Hitchin. And it's the following one. So you take a spinor field for the metric gamma, you multiply it by the function which is just e to the n minus 1 times u. Remember the relation between the two metrics is g twiddle is e to the 2u times g. Then you apply Dirac for, so this is still gamma spinors, and then you can apply Dirac. Then you do the usual construction of, transforming a gamma spinor into a gamma twiddle spinor, which is this C gamma gamma twiddle. And then you have a nice formula which relates to, if you had done the construction the other way around, you start with a spinor psi, which is a gamma spinor. You make it a gamma twiddle spinor by C gamma gamma twiddle. But then you have to apply to it the Dirac operator for gamma twiddle. And then the two are related by this. But you see here you have n minus 1 over 2. Here you have n plus 1 over 2. So this is the what is called the conformally covariance of Dirac. That is, you have to take spinors with a certain weight if you want the right equivalence between the Dirac operators. If not, you have a shift of e to the n minus 1 over 2 into e to the n plus 1 over 2. But actually, this leads to very interesting consideration from the Riemannian point of view. In Riemannian geometry, there is a very well-known important Laplacian modification of the usual Laplacian, which is delta, by adding, putting a coefficient in front of the Laplacian and adding the scalar curvature. And it is known that this operator is actually conformally covariant. So in a very similar way as my formula before, it means if I take a function, multiply it by e to the n minus 2 over 2, apply the conformal Laplacian for g, it's the same as taking the function u, applying the g twiddle conformal Laplacian, and then there's a factor in front which replaces the e to the n minus 2 over 2 by e to the n plus 2 over 2. And therefore, using the conformal covariance of this conformal Laplacian, one can prove a number of inequalities between eigenvalues. So one result, which was obtained by Usama Ijazi, he proved that for n at least 3, then you have the following property. If you have an eigenvalue of Dirac, lambda gamma, the square of this eigenvalue is at least the quantity n over 4 times n minus 1 Cg, where this is the lowest eigenvalue of the conformal Laplacian, capital C. And equality occurs between these two numbers only if there is a killing spinor. So the killing spinors appear naturally when you want to saturate this lower bound for the eigenvalues of Dirac, which is not so surprising. You remember when I looked at the variation of the eigenvalues of Dirac, then I got as a formula for the variation something which involved actually the Penrose operator. And actually, it's exactly when you have a killing spinor that this operator can be 0. So now, my final point is, we made some progress toward the spinoidal geometry. So I think we did, and because I showed that a number of very natural geometric questions in Riemannian geometry can be analyzed using spinor fields and Dirac operators and Penrose operator. One thing which has been very important has been the linkage with the Ricci curvature, and my own feeling is that one should understand even better the Ricci curvature using more the spinors. Actually, this is something that Andrei Lichnowitz kept repeating to me. To understand Ricci for good, you will need to really think of this in spinorial terms. As I said, and you've seen that from my lecture, mathematicians have basically looked only at spinor fields of spin 1/2. That is what I call spinor fields. Of course, physicists know that they have to use not only spinor fields of spin 1/2, but also 3/2, 5/2, and so on. And probably mathematicians should really pay more attention to these more general objects. And then, of course, as there is a natural operator, which is the Dirac operator on spinors of spin 1/2, there is also the Raritas-Schwinger operator, which is a natural operator for spinors of spin 3/2. And this is the book we just finished. It has been a very collective work. It started a long time ago. As for any book, quite often takes years to finish. This one took 7 years, so it was a long long effort, and I'm very grateful to all the collaborators there, who have been, 3 of them have been my own students, but then they have developed their own work independently. Thank you very much.
Jean-Pierre, thank you very much for teaching lecture, and we have time now for some questions from the audience.
In the infinitesimal formula, how are you addressing multiplicities? Is that included?
Sorry?
In the infinitesimal formula, so that derivative at t equals 0.
Yes.
That of yours, how do you handle multiplicities? Because typically when you're...
No, sure, of course. The difficulty, the eigenvalue is differentiable provided the multiplicity is constant. So if the multiplicity jumps, of course, you're in trouble. So you have to either use some argument with analyticity, and therefore you can follow some branch, or you are really, you have to really look at the subspaces corresponding to the, so these formulas can only be valid if the multiplicity is constant. So if the multiplicity jumps, you have to use ad hoc solution to deal with that. Absolutely, I should have said it, yeah.
Well,
Eigenvalues are not differentiable if you have crossing, yeah.
so, more questions or comments? Well, if not, we thank again our speaker. Thank you very much.
Thank you.
And we're invited for a reception outside.